Let's start now.
Solar wind, the invisible storm. Right now, while you're sitting in front of your screen, something invisible is hitting you. The sun is constantly firing streams of charged particles, electrons, protons, and plasma, in every direction. Not occasionally, not in bursts, but continuously. This is called the solar wind. It travels at speeds of up to 1 million miles per hour, and it has been happening non-stop for 4.5 billion years. Think of it like an endless hurricane in space, one that never calms down, never stops, and never misses. This wind spreads across the entire solar system, pushing outward in all directions until it forms a massive bubble around everything we know, every planet, every moon, every spacecraft we have ever launched. That bubble is called the heliosphere. It extends far beyond the orbit of Pluto, roughly 100 times the distance from Earth to the Sun. It acts as a protective boundary between our solar system and interstellar space, shielding us from the harshest radiation that flows between the stars. In 2012, Voyager 1 crossed that boundary, becoming the first human-made object to enter interstellar space. And even then, it was still being hit by solar particles. But here's the part most people don't realize. The solar wind isn't harmless. It destroys. Mars once had a thick atmosphere. It had rivers, lakes, possibly even oceans. Geological evidence suggests it was a warm, wet world billions of years ago, a world that might have been habitable. But unlike Earth, Mars didn't have a strong magnetic field to protect it. So for billions of years, the solar wind slowly stripped its atmosphere away, particle by particle, until almost nothing was left. Today, the Martian atmosphere is less than 1% as dense as Earth's. The surface pressure is so low that liquid water cannot exist. The temperature swings from 20 degrees Celsius at the equator to minus 125 at the poles. Today, Mars is a frozen, airless desert. NASA's MAVEN spacecraft confirmed this, spending years measuring the exact rate at which the solar wind still strips Martian atmosphere today. Around 100 grams per second, every second. Still happening. Earth avoided that fate because of one thing: its magnetic field. This invisible shield deflects solar particles around the planet, bending their paths away from the atmosphere and funneling them harmlessly toward the poles. Remove it, and Earth wouldn't be destroyed instantly. It would simply become the next Mars. Slowly, quietly, completely. Solar flares. When the sun breaks. What we just described is the sun on a calm day. But sometimes, the sun loses control. And when it does, it explodes. These explosions are called solar flares. A solar flare happens when the sun's magnetic field becomes twisted and unstable, and suddenly snaps back, releasing an enormous burst of energy in a fraction of a second. The amount of energy released in a single large flare is roughly equivalent to 1 billion hydrogen bombs detonating simultaneously. Unlike Earth, which has a relatively stable magnetic field, the sun is made entirely of plasma, a superheated, electrically charged fluid that behaves like no solid or liquid on Earth. It has no fixed surface. It flows, it churns, and it doesn't rotate evenly. The equator spins faster than the poles, completing a rotation in about 25 days, while polar regions take 35. Over time, this differential rotation twists the sun's magnetic field lines into tighter and tighter coils, like twisting a rubber band past its breaking point. When that tension finally releases, the result is a solar flare. But here's what makes it truly dangerous. The energy doesn't come as heat. It comes as radiation, X-rays and gamma rays, traveling at the speed of light, which means it reaches Earth in just 8 minutes. No warning, no delay, no time to react. Solar flares are classified into 3 categories: C, M, and X, with X being the most powerful. Within the X category, the scale continues upward with no theoretical ceiling. In 2003, during what became known as the Halloween storms, scientists recorded a flare that reached X28 before the measuring instruments were overwhelmed and stopped functioning. We never determined how strong it actually became. In 2024, the strongest flare in 2 decades, an X9, briefly disrupted radio communications across large parts of Earth's surface. And according to multiple independent studies, our Sun is capable of producing something far worse: a superflare potentially 100 times more powerful than anything in the historical record. The only question is when. CME, when the Sun throws matter. But a solar flare is just radiation. The real danger comes next. Coronal mass ejections, CMEs. If a solar flare is like the Sun firing a gun, a CME is like the Sun throwing an entire car. A CME is a massive cloud of magnetized plasma, sometimes carrying billions of tons of charged material, ripped from the Sun's outer atmosphere and launched into space at speeds ranging from a few hundred to several thousand kilometers per second. And unlike radiation, which is pure energy, this is physical matter. A wall of magnetized plasma the size of several Earths, moving at a significant fraction of the speed of sound in space, headed directly for our planet. When a CME reaches Earth, it doesn't slide past quietly. It collides with our magnetic field, compressing it on the side facing the Sun and stretching it dramatically on the night side. The field that normally sits about 65,000 kilometers above the surface gets pushed down to 20,000 kilometers or less during a powerful impact. And a violently shifting magnetic field generates something dangerous: electrical currents. Everything in Earth's power infrastructure, power lines, long-distance transmission cables, oil and gas pipelines, acts as a conductor. When a CME distorts the magnetic field strongly enough, it induces massive, unexpected currents throughout all of that infrastructure simultaneously. Not enough to trip a standard circuit breaker, enough to catastrophically overheat and melt the large transformers that are the backbone of every national power grid. Those transformers are not off-the-shelf components. They are custom-engineered, individually manufactured pieces of equipment. A single unit can weigh over 400 tons. Lead times for manufacturing and delivery can stretch to 12 to 18 months under normal conditions, and that assumes the factories producing them haven't been affected by the same event. One of the fastest CMEs ever recorded reached Earth in under a day, and it missed us. But on July 23, 2012, something even more alarming happened. A CME as powerful as the most destructive geomagnetic event in recorded history passed directly through Earth's orbital path. We missed it by just 9 days. Had Earth been at that position 2 weeks earlier, scientists at the University of Colorado estimate the damage could have exceeded $2 trillion, with some models projecting recovery times of 4 to 10 years for developed nations, and far longer for countries without the industrial infrastructure to replace critical components. And our early warning system for this kind of event is extremely limited. The primary sensor, a satellite called Discover, sits about 1.5 million kilometers between Earth and the Sun. When it detects an incoming CME, the average warning window is somewhere between 15 and 60 minutes. For an event capable of reshaping civilization, 15 minutes. Geomagnetic storms. The damage. When a CME strikes Earth, the result is called a geomagnetic storm. The CME is the impact. The storm is everything that follows. These storms can persist for hours, or stretch across multiple days, during which time the distorted magnetic field continues generating unwanted currents and interference throughout every electrical system on the planet. The most well-documented modern example happened on March 13, 1989. A geomagnetic storm struck Quebec, Canada. In less than 90 seconds, the entire provincial power grid collapsed. Not gradually, instantly. Automatic protection systems designed to handle normal faults were completely overwhelmed. 6 million people lost power in the middle of a Canadian winter. The outage lasted 9 hours. Heating systems failed. Hospitals switched to emergency generators. The economic damage ran into hundreds of millions of dollars. And that was from a storm that, by historical standards, was not even close to the largest ever recorded. During the same event, auroras appeared as far south as Texas, Cuba, and even parts of Central America. Satellites experienced unexpected drag. Radio communications were disrupted across wide regions. And this brings us to something that rarely gets mentioned in discussions of solar weather. Auroras are not just beautiful. They are a warning sign. Auroras occur when solar particles break through Earth's magnetic defenses and collide with atmospheric molecules near the poles. The light you see is those molecules releasing energy as they're struck. The brighter and more widespread the aurora, the deeper the penetration. When auroras appear at tropical latitudes, it means Earth's magnetic shield has been significantly compromised. The ecological effects are equally underappreciated. Dozens of species, including migratory birds, honeybees, sea turtles, and whales, use Earth's magnetic field as a navigational compass. Geomagnetic storms scramble that compass. Studies have documented significant increases in whale strandings during periods of intense solar activity. Satellite tracking data for migratory birds shows disrupted flight paths during geomagnetic events. The biological web that depends on magnetic stability is far larger than most people realize. The Carrington event. The worst case. Everything described above is context for one central question. What happens when all of it hits at once, at maximum intensity? We already know. It happened on September 1st, 1859. An amateur astronomer named Richard Carrington was sketching sunspots when he observed something no one had ever seen: a sudden, intense white light erupting from the sun's surface. He was watching a solar flare in real time with his naked eye. Roughly 17 hours later, far faster than most CMEs travel, Earth was struck by the most powerful geomagnetic storm in the modern record. The response was immediate and global. Auroras erupted across the entire planet, visible at the equator, in the Caribbean, in Colombia. The night sky was so bright that miners in the Rocky Mountains woke up and began making breakfast, believing it was dawn. Telegraph systems, the most advanced communications technology of the era, failed completely across North America and Europe. Operators received severe electric shocks from their equipment. Telegraph paper caught fire spontaneously. And in one of the most surreal details from that night, some telegraph operators discovered their systems continued to function even after being fully disconnected from their batteries, powered entirely by the induced currents from the storm itself. That was 1859. The global electrical infrastructure consisted of telegraph wires. Today, that same event would strike a civilization whose entire functioning depends on electronics. Power grids, internet infrastructure, GPS satellites, banking systems, hospital equipment, water treatment plants, emergency communications, transportation logistics, supply chains. The estimates for economic damage from a Carrington-level event today begin at $1 trillion, and that figure, developed by the National Academy of Sciences in 2008, is now considered conservative by most researchers. More recent models, accounting for the full cascade of interdependent system failures, place the figure significantly higher, and recovery would not be measured in weeks. Think about what that means in practice. Modern food distribution systems carry, on average, about 3 days of inventory at any given point in the supply chain. Fuel logistics depend on continuous electronic coordination. Financial systems, the mechanism through which societies allocate every resource, run entirely on networked digital infrastructure. A prolonged, simultaneous failure of power and communications doesn't just cause inconvenience. It collapses the organizational layer that holds complex societies together. The physical world remains intact. The systems that allow us to coordinate within it do not. Solar energetic particles, the invisible danger. Among all the threats discussed so far, one is the least visible and possibly the most immediately lethal: solar energetic particles. These aren't waves of radiation like those from a flare. They aren't massive plasma clouds like CMEs. They are individual subatomic particles, protons and heavier ions, accelerated to extraordinary speeds by the shockwaves that follow large solar events. Some travel at 50 to 80% of the speed of light. At those speeds, they don't deflect easily. They penetrate. They pass through thin metal shielding as though it isn't there. They damage biological cells directly, breaking DNA strands and disrupting cellular repair mechanisms. They corrupt electronic components, flipping bits in computer memory, degrading sensors, causing navigation systems to produce silent errors. And they arrive fast, sometimes in under 30 minutes from the triggering event. For astronauts operating outside Earth's magnetic field, on the International Space Station during certain orbital positions, or on any future lunar or Mars mission, a large solar particle event represents an existential threat. Estimates suggest that astronauts caught in the open during a major event could receive a fatal radiation dose within hours. The closest historical brush with this scenario came in August 1972, when an extraordinarily powerful solar particle storm erupted between Apollo 16 and Apollo 17. The timing was precise enough to be disturbing. Had astronauts been on the moon's surface during that event, as they were just weeks before and just months after, the outcome would likely have been fatal. We have been lucky. The window between events and missions has, so far, been wide enough.
Cosmic rays, passing through you right now. Something is passing through your body. You can't feel it, you can't see it. There is no instrument in your home that detects it. But it's happening. Cosmic rays. These are high-energy particles originating from deep space, supernovae, active galactic nuclei, collisions between neutron stars, accelerated across the universe and arriving at Earth from every direction simultaneously. They travel at near the speed of light and carry energies that dwarf anything produced by the sun. Every second, roughly one cosmic ray particle passes through every square centimeter of your body. Over a full human lifetime, trillions of these particles will pass through you. Most cause no detectable harm, but at high altitudes, in aircraft for example, the dose increases significantly, which is why long-haul pilots are classified as radiation workers in many countries. The most extreme cosmic ray ever detected was documented in 1991. Physicists nicknamed it the "Oh my God" particle. It was a single proton the size of a subatomic particle, carrying kinetic energy equivalent to a baseball thrown at 90 kilometers per hour. Concentrated into an object billions of times smaller than an atom, moving at 99.9999999999951% of the speed of light. Its origin remains unknown. We have no model that fully explains how anything in the universe accelerates matter to that energy. It passed through you, or your parents, or your grandparents, without leaving a trace.
Van Allen belts. Earth's hidden radiation trap. Earth doesn't just defend against radiation from outside, it also traps it. Surrounding the planet are two massive donut-shaped regions called the Van Allen radiation belts, zones where Earth's magnetic field captures and holds charged particles in place, causing them to spiral back and forth between the magnetic poles in endless loops. They were discovered by accident in 1958 during the first American satellite mission, Explorer 1. Scientists on the ground noticed that the radiation detectors on board were periodically returning readings so high they overwhelmed the instruments. At first, the team assumed the equipment was malfunctioning. It wasn't. The satellite had passed through a zone of trapped radiation so intense it exceeded what the detectors were designed to measure. During solar storms, the Van Allen belts swell. They absorb the incoming charged particles from CMEs and solar flares, intensifying dramatically. This surge can damage satellites passing through the outer belt, degrade solar panels, and inject additional radiation into orbital regions that are normally considered relatively safe. Any future mission that sends humans beyond low Earth orbit, to the Moon, to Mars, or further, must pass through these belts. Managing that transit is one of the least discussed but most serious engineering challenges of deep space exploration. The solar cycle. It's about to get worse. None of what we've described happens at a steady rate. It follows a rhythm, a deep, predictable pulse embedded in the sun's behavior. Every 11 years, the sun moves through a complete cycle, transitioning from a period of relative quiet, called solar minimum, to a period of peak activity, called solar maximum. During solar maximum, the sun's magnetic field reaches its most chaotic and unstable state. Sunspot numbers climb significantly. Solar flares become more frequent, more intense, and more capable of delivering powerful bursts of radiation across the solar system. Coronal mass ejections, CMEs, are launched more often and with far greater energy than during quieter periods. The transition between minimum and maximum is not gradual or gentle. Activity can spike sharply and unpredictably as the cycle approaches its peak. The most recent solar minimum occurred in late 2019. The current cycle, Solar Cycle 25, was initially predicted by scientists and space weather agencies to be moderate, perhaps even below average in intensity. That prediction has proven to be significantly wrong. The sun has been far more active than anticipated, surprising researchers with the frequency and power of its outbursts. In 2024, Earth experienced its strongest geomagnetic storm in 2 decades, driven by a series of coordinated CME impacts that compressed the planet's magnetic field to historically low altitudes, triggering widespread aurora sightings and raising serious concerns about infrastructure vulnerability. We are currently at solar maximum, the most active phase of the most active solar cycle in 20 years. Superflares. What we haven't seen yet. Everything discussed in this video is based on what our sun has actually done, on real events measured and documented through centuries of scientific observation. Our sun is, by stellar standards, a calm star. Relative to the vast population of stars in our galaxy, it is stable, consistent, and restrained in its behavior. But astronomers studying other stars similar to our sun, same age, same mass, same temperature, have observed events that redefine the scale of what's possible. These are called superflares, eruptions between 100 and 1,000 times more energetic than the most powerful flares our sun has ever produced. They occur on stars that, by every measurable characteristic, look almost identical to ours. The consequences of a superflare from our sun would be extraordinary. The ozone layer would be significantly depleted, potentially by 90% or more in some models, exposing the surface to lethal ultraviolet radiation for years. Communication and power systems would fail globally and simultaneously, with no part of the planet left unaffected. The geomagnetic disturbance would persist for days, prolonging the damage far beyond the initial event. For a long time, scientists believed our sun was too old and too stable to produce superflares, that this was a phenomenon belonging to younger, more volatile stars. Recent research has challenged that assumption. Analysis of stellar data and deep ice core records suggests that our sun has produced superflare-level events at least once in the past 10,000 years, and possibly several times. The evidence is indirect, but it exists. The historical record is simply too short to call it impossible. It hasn't happened recently. That's not the same as saying it can't.
The world is full of hidden stories, and here at Paint Facts, we reveal the most impressive ones. So subscribe to the channel and turn on notifications, because the next fact might just surprise you.